So hello everyone, this is lecture 35 for the mathematical physics. Well, I am having some cold, so please tolerate. So in the last lecture we studied about the CR equations and some necessary and the sufficient conditions for a function to be analytic. Okay, so these were the conditions. Del u by del x should be equal to del v over del y, and del u by del y should be equal to minus del v over del x. And we have seen this example, and this were the necessary condition. Then we said that if these partial derivatives are continuous also, then our function will be means that will be sufficient to call a function as analytic. So first you have to see these equations to verify by a function. Then you will see that if these partial derivatives are continuous or not. Okay, so these are the two ways to find if a function is analytic or not. So let's see. A function is given in the form of u and v. So you can find the df. Df is nothing but, we already discussed about this, it will be del u over del x means differentiation of this with respect to x multiply dx plus this with respect to y then dy. So that's how we can write this df as this. So here we have now we need to rearrange this equation. First, from these equations, the Cauchy-Riemann conditions, del u by del x can be written as del v by del y, or del v by del y can be written as del u by del x. So you can write this, and same you can write del u by del y as minus del v over del x. So it will be written like this. Okay. Now this equation can be written like this, because if you multiply this equation with this, you will get all these terms. This I square dy del v over dx will give you this minus del v over del x dy. So this equation can be written like this. You can just multiply these and you can get this. Okay, so this is nothing but dx plus I dy is nothing but dz. Okay, so take this at the denominator, so we'll get df by dz as this. Now see this is a value of df by dz, so it will be independent of directions, because now we are getting the differentiation with respect to z. Okay, so we will say that if these are continuous, then they are independent of direction of approach. Means if they are continuous, then we will say that function is analytic. Okay, so now we don't need to check the directions whether x y or x equal to y. Okay, now if they are continuous, then the function will be continuous, because this is a direct formula for df by dz. So remember this thing. Now let's see one more thing. We already proved that this z conjugate is not analytic. Now let's see this result from here. Okay, from these equations. So z conjugate is nothing but x minus iota y. So u is x and v is minus y. So use the CR equations. So del u by del x will be 1 and del v by del y will be minus 1. So these are not equal. So we'll say that function is not analytic at any point in the complex plane. Okay, and see the point is here that this function is continuous at every point in the complex plane, but not analytic or differentiable at any point. So remember this thing. We also can use this z conjugate thing in the any function to find if that function is analytic or not. I will tell you how. This will be a very great result. So we already proved that this z cube is analytic. Now see from the CR equation and this if it verifies these equations or not. So z cube is this x plus iota y cube. We just use a simple algebra. Okay, identity a cube plus b cube plus 3a square b plus 3ab square. So we'll get this expression. Now take the imaginary terms out and the real terms out. So you will get u and v. So find del u over del x and del v over del y. They are equal. See, they are equal. So first condition is satisfied. Second condition will be del u by del y and del v over del x will be this. So minus del v over del x equal to minus 6xy. So they are equal. So this satisfies the CR equations. Okay, so now we can see that this and this all are continuous also. So we will say that this function is analytic. Okay, so we already proved that all the complex functions with the polynomial or the power of integers, so they all are analytic. So we just verified this. So let's see we were having z cube, then we can use the direct formula. But if there is z to the power 6 or means higher terms, then how can you solve that? So you will use the binomial expansion. You know how to expand a binomial expansion. It will be, if it is n, then you will take nc0, x to the power n minus 0 and y to the power 0. Then again next term will be nc1, x to the power n minus 1, y to the power n. So that's how you will go up to n. Okay, so that's how you can expand. Try to expand this and take the imaginary and the real terms separate. So I am writing the direct results. U will be this and V will be this. So now let's check if they satisfy the CR equations. So del u by del x equal to del v by del v, we get the same result, and this was also equal. So we say that this function is also analytic. So we already know that this came out to be analytic because this is the integer power of a polynomial. Now let's see this thing. Means we know that z conjugate is not analytic at any point. So how we can see this thing, and we can say that if any function involving this z conjugate, then we say that that function is not analytic at all. Okay, so that's how we will use this z conjugate. Let's take an example. If fxy equal to mod x minus iota mod y. Now in the fourth quadrant of the complex plane, let's check where it will be analytic or not. This function. So in the first function we know that x is greater than 0, y is greater than 0. So we can write this function as x minus iota y. Now see, this is nothing but z conjugate. So this will be non-analytic in this reason. Definitely, because this is z conjugate, so this function is non-analytic, we know that. Now in second reason, x is less than 0 and y is greater than 0. So if x is less than 0, then this can be expanded as minus x minus iota y. You know that mod x will be written as minus x for the x less than 0, so that we can get positive here. So we'll get for this quadrant minus x minus iota y. Now take the minus common, you will get x plus iota y, that is z. So minus z. So this will be analytic because this is not involving z conjugate, and we know that z is analytic. Now in third quadrant we have x less than 0, y less than 0. So both will have minus x here and minus y here. So it will give you minus plus, and here is minus x. So this will be your function in third quadrant, and this is nothing but minus z conjugate. So this will also not be analytic because this is z conjugate function. Now in the fourth quadrant, let's see. Here x is greater than 0 but y is less than 0. So it will be x minus y. So we will get x plus iota y. So this is z and this is analytic. So that's how you can check a function involving z conjugate, then that will be non-analytic, otherwise analytic. Let's see some more examples because this is very helpful in the exams. This function is given. Now see, this x minus iota y is nothing but z conjugate. So so this whole function will be non-analytic. We can directly see this example, and we can say that this is non-analytic. In this we say that this is z and this is also z because take the minus common. So this function will be analytic because there is integer power, and it will be a polynomial. Now here take the minus common, it will be z, and take the minus common, it will be z conjugate. So this function involves the z conjugate, so we'll say that this function will be non-analytic. Now this is z here, and but we are having a fraction power. So wherever you are getting fractional power, you will say that this function is non-analytic because there will be some singularity points we will getting, means where this function is not non-analytic. We will study about it further, but here just remember, if you are getting fractional power and inside z, then it will be non-analytic. Let's take these. You have these four options. You have to check that which one is analytic or which one is not. Okay, so here you involve z, and it will be square of x plus iota y. So it will also be z square. So it will be analytic. And now take minus common, it will be z here. So it will be also analytic. Now this is also z square minus 3. So it will be analytic again. But here if you take minus common, you will get z conjugate. So this will be non-analytic function. Now there is a very useful result from the CR equations, means using one imaginary or the real part, we can find the another one. Okay, means if u is given, you can find v, and v is given, you can find u. If that function is analytic, then you can find them using the CR equations. Let's see how. Real and imaginary part of an analytic function satisfied Laplace equation in 2 dimensions. So first, this is the result. Laplace equation for the wave means harmonic oscillator. So they satisfy the condition. Okay, these conditions means analytic function satisfies these conditions. So these are nothing but this: del square u by del x square plus del square u by del y square equal to 0, and this equal to 0. You can prove them easily, very easily, using the CR equations. Means we have this first equation, and you just derive, take the derivation again with respect to y. Then you will get del square v by, sorry, take the with respect to x. So del square u by del x square, and here it will be del v by del y del x. Now using the second CR equation, take the y respective, and you will get this value. So in place of this, write this del square u by del x square, then take it to the left hand side, you will get this equation. So same you can find this equation also using the CR equations, and we know these are the Laplace equations, so they satisfy these equations also. That's why we call these u and v are harmonic functions. Here v is called the conjugate harmonic of u. Okay, so if in some question it is given that find the conjugate harmonic, so you just need to find the real. If real is given, then you need to find the imaginary part, and if imaginary is given, you have to find the real part. Okay, so remember this result. If u equal to xy, so let's take an example. If u is given xy, then we need to find the conjugate harmonic. The means we need to find the v. So using the CR equations, we know del u by del x should be equal to del v by del y. So del u by del x will be y, and from this equation we can see del v equal to y del y. So integration will give us this, means there will be some constant hx also, and that constant will be function of x. Why? Because now if you take the derivative of v with respect to y, so you will get del v over del y equal to something from here, and this will be 0. So you will get again this equation. That's why we are taking this constant as a function of x. Okay, because if you take the differentiation with respect to y, then this will term will cancel out to 0. Okay, so now v will came out to be, integration will give us y square by 2 plus hx. So now we have v, but we don't have the value of hx. So to find the value of hx, we use the second CR equation, that is del u by del y equal to minus del u over del x. So del u over del y is nothing but x, so this should be this. From here del v will be minus x dx, so it will give you minus x square. So see, this del u over del x you can find from here, because this is v. Now del v over del x will give you 0, and del h over del x. So this will be del v over del x will be equal to del h over dh over dx, because now this h is function of x only, so we can write the complete derivative. So dh over dx equal to x, so this will give us minus x dx. So h will be minus x square by 2 plus some constant k. Now it is constant, is not a function of anything. So now you have a value of h, so you will substitute this whole term here, so you will get the value of v. This k also can be found if there is some initial conditions are given. We'll see the example of that also. So here you get the v now. For now you have v. Just substitute this value here in the place of hx. So y square by 2 minus x square by 2 plus k will be your v. Let's take one more example. If u is given x square minus y square minus y, we need to find the v. So using CR equation, del u by del x will be 2x equal to, that should be equal to del v over del y. From here v can be equal to 2x del y. So this integration will give you 2x del y will give you 2xy plus some constant, that is a function of x. Okay, so v will be this. Now we need to find this hx. So we use the second condition. So del u by del y should be equal to minus del v over del x. So from here you can find the del v over del x. So it will be 2y plus del h over del x and the minus sign. Now this will be equal to this. Now if you expand this minus sign inside, minus 2y minus del h, dh over dx. So minus 2y will cancel out, and you will get dh over dx equal to 1. From here h can be written as x plus some constant k. Now you have h value, so you can substitute here. So v will be 2xy plus x plus k. So we studied this thing in the differential equation also, so you can see those lectures, then you will be better understand how we are doing this. And still I explained it again also, so it is very easy thing. Now let's take one more example where we will find this constant also. The imaginary part of an analytic complex function is this. Now v is given, the real part of the function is 0 at origin, so u at 0 0 is 0, this is given. We need to find the value of real part of the function at 1 1, okay, 1 plus iota. So for that we need to find first u. What is u? So we use the CR equations. Del u by del x should be equal to del v over del y. So del v over del y will give us 2x plus 3. Now from here you can find u equal to 2x dx plus 3. So it will give you this equation plus some constant that will be function of y now, okay, because we are taking partial differentiation integration with respect to x, so we will get a constant as a function of y. You can see if you take the del u over del y, del u over del x now, so you will get this term as 0 and again this term. So that's why we have taken this constant function as a function of y. So from here you will get x square plus 3x plus this hy, so this will be your u. Now you have u, but this hy is still variable, so you need to find this value of hy. So for that you will use the second condition, del u over del y. So del u over del y, if you differentiate this, you will get 0 here and del h over del y. And from the CR equation this should be equal to minus del v over del x. And what is del v over del x? From here it will be 2y, so 2y and minus sign will give you this. So you have dh over dy equal to minus 2y. From here dh will be minus 2y dy, so it will give you minus y square plus some constant k. This is not a function of anything because we are having only one variable now, that's why we have complete derivative. So this is hy, so substitute this hy here and you will get your uxy. So this is your uxy finally. Now you can find the value of k because the initial conditions are given. The real part of the function is 0 at origin, so at x equal to 0, y equal to 0, this uxy is 0. So 0 0 will give you k equal to 0 from here. So substituting k equal to 0, you will get your uxy as x square plus 3x minus y square. Now you need to find the value of that function at 1 plus iota. So it will be x will be 1, y will be 1. So 1 square will give you 1 plus 3 minus 1. So 3 plus 1 4 minus 1 will give you 3. So u11 will be 3. So this will be your answer. So okay, that's it for today. In the next lecture we will discuss the polar form, okay, of this differentiation and all, and we will discuss some methods. So that's all for today. Thank you everyone.